Okay, this is going to be the video for differential equations 8.2, the last section on day 4, which we're going to talk about graphing all this stuff with phase portraits. So, okay. All right, so let's go ahead and take a look. Remember 1D phase portraits? Earlier on in the differential equations course, we said that if we happen to have an autonomous differential equation, just a single differential equation, what makes it autonomous is that your right-hand side is a function of only the dependent variable, so something like this. And what that means is if you were to plug different values for p in, since the p is the dependent variable versus, say, t, then you would have the same slope, right? This gives you the slope, the instantaneous rate of change of the solution curve at that point. And because there's no t on this side of the equation, whatever slope you get, it's the same for all the different independent variables, all the different t's. So the slope field would be, the same, consistent as you move from left to right. And then we said that you could solve for which values of the dependent variable, in this case p, make the right-hand side 0, and those are called the critical points. Like this particular one is 0 when p is 0 and p is 2. And so if you just did an axis here for the y variable, p in this case, then you could split it apart at these critical values, and those are the places where the slope is 2, right, where the slope field would have a horizontal curve. And then we could try some values, like we could try a value like 1 or -1 or 3, and plug that in the right-hand side and to just determine whether or not the slope is positive or negative, because it can only change direction as we cross over those critical points, right? So then we learned behavior. We said, well, if this is going to be a negative slope in the top here when p is above 2, then we put a downward arrow here, just indicating that any curve as we go from the right has to have a downward slope as it approaches this value asymptotically. And the same thing here, we'll have positive slopes, so they will approach the two critical values asymptotically. And then anything where we start with a p that's below 0 would end up having a negative slope that diverges from that, right? So these horizontal lines form kind of stable points at the critical points, where eventually the solution will align itself with those values. Okay, so this is called a 1D phase portrait or 1D phase diagram or a phase line. Okay. But the restriction here is that you can only have just the y variable, just the dependent variable on the right-hand side. Well, now we're saying we have a whole system, right? And we have x and y as a function of t, right? And when we're done, we can plot a phase diagram that plots x versus y. But in general, those slopes might not be the same for all x's and y's. So let's take just an example system here. We have an example system. We can put it in matrix form. Maybe we're given an initial condition, and then we can solve this system for the system solution. We would first solve for the eigenvalues. This particular one using the procedure has an eigenvalue of -1 and a 4. And then for each of those, we would find an eigenvector. Since they're two distinct real ones, we have two separate eigenvectors. We go through the procedure, and we get -1, 1 for the eigenvalue -1, and we get the eigenvector 3, 2 for the eigenvalue 4. Right, so then we could form the general solution, which would be C1 times the first eigenvector times e to the -1t plus C2 times the second eigenvector times e to the -4t. And then if we are given an initial condition like this, then we can go ahead and plug that in, because this is saying that x when t is 0 is 2 and y at t at 0 is 3. You could plug those in here to get the two equations, and eventually and use the system solution method to solve for what C1 and C2 are. In this case, they both happen to be 1, and so that means this right here is the general. This is the specific solution that goes with this initial condition. Okay, and what that is two separate equations. Since this is a matrix, this is x as a function of t is negative e to the -t plus 3 e to the 4t. But y as a function of t is positive e to the -t plus 2 e to the 4t. Right? So you can say, all right, we should be able to, on an xy plane, do a 2D phase portrait that shows as we vary t, what is the x and y. We can treat this as a position vector, essentially, right? Okay, so if we have these specific things, it's almost like we're defining a position vector with the parameter t, and we're saying that negative e to the negative t plus 3 e to the 4t is the x, and e to the negative t plus 2 e to the 4t is y. And we can plot that the same as we did in Calc 3. So this is just a parameterized curve. And so we call that a trajectory. And because we had the initial condition that x at t is 0 is 2, 3, then that means that t equals 0, we're at this point, and it's going through that initial condition point. So we have the particular trajectory that goes through that point. All right, so we kind of know how to do this. We saw that earlier. And then what we said is, if you were to then take a whole bunch of other different initial conditions, and then for each one solve for C1 and C2, then you would get different curves, right? And you'll have an entire family of curves, depending on what your initial condition and the corresponding C1 and C2 is. And so if we plot many of them on the same graph, then it's called a phase diagram or a 2D phase portrait, okay, something like this. So we're going to just look at this kind of qualitatively and see what we can see. One thing I notice is that regardless of where you start in the XY plane, unless you're right on this, this kind of negative slope diagonal line, you're going to pretty quickly eventually align yourself to one of these, this positive slope red line, this asymptote. And so those particular values are stable, right? If we had, let's say, let me pick a different color, green here. Let's say that I started here. If I started here, eventually I'm going to find some sort of a pathway which aligns itself with this stable location, right? It's going to align itself that way. On the other hand, if I start with an initial condition down here, it will eventually align itself with this stable value. And those are really the only two kind of areas where we have stability. If we're not at those places, then we would have a system that's not stable. But we're not going to eventually align ourselves to here, right? Eventually, as we move far away from the origin, we're going to align ourselves to one of the stable values. Now, one thing that's kind of interesting is if you look at the eigenvectors for this system, it was -1, 1 and 3, 2. Those happen to be, if you plot them as vectors from the origin, those happen to be pointing in the direction of these two asymptotes, interestingly. All right, so if we wanted to know the direction, we have to carefully note what happens as you increase t. So you'd have to see, do you go, like on this line, you're going this direction as you increase t. But on this line, as you go from t equals 0 to 1 to 2, you're going in this direction. So not only is there a curve, but there's a direction along the curve that you determine by plugging in ever-increasing values of t. All right? All right, so this is kind of an example. Let's take another example, a second example. Here's a system, looks pretty similar to the first example. We put it in matrix form, maybe we specify initial condition. We solve for the eigenvalues, and in this case, we end up with a non-factorable characteristic equation. So we have to use the quadratic equation, quadratic formula, and we get complex conjugate pair, which means we take the positive version, and then we do that more complicated thing to find the eigenvectors. We can find an initial complex eigenvector here, k, by picking one of the equations to work with. I picked the second one in this case to work with. And we get 1 plus 8i, and then for the x and then the y constant there, k2 is 5. Right? And then you have to build the solution from finding separate vectors b1 and b2 with the real and imaginary parts. So the real part would be 1, 5. Imaginary part would be 8, 0. And then you would say the general solution vector is C1 times B1 cosine minus B2 sine times e to the alpha t plus C2 times B2 cosine plus B1 sine times e to the alpha t. And so when you put it all together, you get this. This is the general solution. It involves a lot of cosines and sines. And also this e to the 2t, which means as t increases, everything is going to eventually get larger and larger and larger. So if you were to plot this, because there's really two equations here, right? There's an equation that says, well, first we have to establish the constant. So if we have an initial condition, like when t is 0, x is 3, but y is -10, you could plug those into the two equations and then use the system to figure out that the constants, in this case C1 is -2 and C2 is 5/8. Then you can plug those in here to get the specific solution that goes through that initial condition. But what would the phase portrait or the phase diagram look like for this? Well, I want to show you something in your calculator that you maybe you've encountered this, but since this is essentially a parametric equation, we can use the parametric mode of our calculator to graph this. So I wanted to show you what that would look like. Looks like I'm going to have to make some gains here to do this on this board. Try that again. Okay, we'll put that up. And all right, so what you can do is you can take these equations and plug in the x and the y equation separately, but first you have to put your calculator in a different mode. So if you press the mode button on a TI-83 or an 84, right below radian and degree, there's different modes. Normal mode is function mode, but if you go over here, there's parametric mode, and then there's also polar coordinates mode. Let's use this PAR, parametric mode. When you switch to parametric mode, if you go to y equals and you enter an equation, you're going to see that there's a separate line for the x and the y. And that's going to be in terms of the parameter t. So when I press the variable button, I'm going to get a t. So that means I would enter this equation, this set up here at the top. So let me go ahead and type that in. For x, it's going to be the top row. So that's going to be entered as -2. And then I'm going to go ahead and put a parentheses there and enter it just like that. So it's going to be cosine of 8, and then the variable key, which is going to put the parameter t in there, minus 8 times sine of 8t. Okay, close. Oh wait, did I close the parentheses on the cosine? I don't think I did. Let me do that again. Clear that. It's -2 parentheses cosine 8 times the variable key, close parentheses to shut down the cosine, minus 8 times the sine of 8 times the variable key, and then a parentheses to close that. And then that whole thing is times e to the, so I'll go e to the x, not natural log, let me go back, e to the x, second, there we go, e to the x, 2 parameter key. That's this first thing with the C1. With the C2 term, it's going to be plus, so plus 5/8, and then times, and we'll do a parentheses here, it's going to be 8 times cosine of 8t, close the parentheses on the cosine, plus the sine of 8t, close the parentheses on the sine, close the parentheses on the quantity, times e to the 2t. Okay, so that is the equation for the x. And then we can put the parametric equation for the y in there. So by doing the bottom row here, this is going to be -2, and then we've got parentheses, and we've got 5 times cosine of 8t, close the parentheses for the cosine, close the parentheses, period, times e to the 2t. Okay. And then for the second term, we've got plus 5/8. So let me put 2t back in there again, and then down off the line, plus 5/8 times the parentheses, and this time it's going to be 5 times sine of 8t. Close the sine parentheses, close the parentheses, and then times e to the 2t. Okay, so if you carefully enter the x and the y rows separately, then you can plot this. Now, before we actually plot it, it's important that we set the window, because this can get kind of out of control, and if you don't set this appropriately, it can take your calculator like 5 minutes to graph it. So let me show you something that will work for this particular plot if you're doing this with me. You can go to your window button. You want to set the minimum time to 0, the t to 0, and then let's just go up to a t max of 1.5. That'll keep it reasonable. If you go up to like 2 pi or anything, it starts getting pretty long. And then for a step size, I want this to be fairly accurate. So instead of the default that's coming up with 0.13, let's make t go up by 0.01 each time. Okay, and then we need to set the scaling for x and y on the plot. So I'm going to have x minimum start all the way down at -150 and go to a max of +150 with a scale of 1. And then I'm going to go down here to y minimum and put -150, and then +150 with a scale of 1. Okay. So we've got that. Next thing we're going to do is we're going to say zoom. Okay, so let me quit out of that. And I'm going to say zoom, but instead of zoom like standard, I'm going to say the 5th item, zoom square. Because what that will do is it'll reconfigure the t or the x and y max and min so that it's the same physical distance as you go from left to right. So it'll overwrite my x and y maxes to get close to that, but in a way that's square. So you can see what's doing here. It's having t go up by 100th every time, and it's slowly graphing the xy points to that into that position vector. And so we're getting a spiral shape, right? And I can kind of see the reason I went ahead and added this blue arrow over here on the notes is I could see as it was drawing what direction we were traversing this trajectory as we increase t. Right, so that's what that would look like, and you can put your calculator in parametric mode to be able to graph that way, where you enter separate x and y in terms of the parameter t. Okay, so that particular one does go through this initial condition, point 3, -10. It might be hard to find that, but if I were to put a trace on here, yeah, sure enough, at x is 3, y is -10, there's that point here, and as I move this, it's going to move along the curve to different places, right? But one of the points that it goes through is, in fact, 3, -10. Okay. All right, so that was interesting. And the reason why it's a spiral, it keeps getting larger, is because of these e to the 2t terms. Because as t increases, this exponentially gets larger and larger and larger. Right? The circular behavior comes from, we know from Calc 3, the parameterization of circles involves sines and cosines. Okay. If we were to change the initial condition to something like 2030, then the constants would change to, say, -2 and 11/4. And if you were to carefully go update that, I did that in the calculator, and it just adds a different spiral, but the radii are a little bit different. So the second curve is slightly different, but with the same general form. Right, so there's really no direct stable location, right? This just keeps getting bigger and bigger as t improves, or t gets larger. So there's some books and online information that I found that try to label what's going on here. There's terms like asymptotically stable, and sometimes they identify structures of these phase portraits as nodes or centers or improper nodes. Our book doesn't do any of that, and it doesn't seem like there's a lot of consistency necessarily between the different labeling of the different sources I found online. So I guess I would just leave you with, you can plot this and then just observe the behavior, right, rather than trying to label it. See what's happening and see if you can see that there's any kind of stable system placed there. All right, so we're going to finish this by just doing one of these by hand. So I'm going to ask that you go ahead and pause the video and then attempt to do this. So solve this system, which means you'll have to put it in matrix form, find the eigenvalues, find the corresponding eigenvectors, and then plug in the initial condition to solve for the constant C1 and C2, and then go ahead and enter this in the calculator in parametric form to graph the phase portrait of this. And this is a suggested setting for the windows to make it look nice. Okay, so go ahead and pause the video and try that, and then you can unpause and I'll show you the solution. Okay, so assuming that you've had a chance to try this on your own, let me go ahead and do this this completely. We've got the system here in matrix form. We would write it like this. So let me do that here in black. We've got x prime is going to equal the coefficient matrix 2, 8, -1, -2, x, and this is homogeneous, so there's no extra stuff out here. All right, so then we're going to find the eigenvalues by doing the determinant 2 minus lambda, 8, -1, -2 minus lambda equals 0. All right, so that's going to give you 2 minus lambda times -2 minus lambda minus -8 equals 0, which when you multiply out and combine them as 8, you end up getting lambda squared minus 4 lambda plus 8 equals 0. Right? Let's see. No, actually, I take that back. This ends up being lambda squared, let's see, minus 4 plus 8. So actually, we just get lambda squared plus 4 equals 0, which means that that lambda squared is just -4, so lambda is plus or minus the square root of -4, so it's going to be plus or minus 2i. So I have a complex conjugate pair. We happen to have alpha is 0, right? So this lambda is 0 plus or minus 2i, and so alpha is 0 and beta is 2. Okay, to find the corresponding eigenvector, let me use a different color here. I'll use purple here. So we're going to pick the positive version. Lambda is 0 plus 2i. And we're going to plug that into this matrix. So we're going to say, okay, it's 2 minus lambda, which is 2i, 8, and then -1 and -2 minus lambda, which is 2i, and then 0, 0 out here. Right? And then we'll go ahead and compute this equation. So I've really got the equation, yeah, just 2 minus 2i, 8, 0, and negative 1, negative 2 plus 2i. I guess I could write it that way, 0, if I factored out the negative. So I could use either one of these equations. Let's use the second one, because the second one, I don't have this extra 8 in it. So I'm just going to say this is negative 1 times k1 minus, and then it's going to be 2 plus 2i, k2 equals 0, which means if I move this to the other side, k1 is equal to negative 2 plus 2i, k2. Okay? And that means that the general solution form is, as long as I make this negative 2 plus 2i times whatever I make k2 and this k2, we've got an eigenvector. So what I could do is choose, maybe I'll just choose, well, I don't know. You know, if I wanted to have a positive value, let's just make this negative 1 so that this negative goes away here, and I can just write this as 2 plus 2i. So you could either be negative 2 minus 2i and positive 1, or we could just make it negative 1, positive 2 plus 2i. Okay, that means that my b vector, my b1 vector is the real part of that, which is 2, negative 1, right? And then my imaginary vector b2 is the 2, 0 vector. Right, so we've got that. And then that means the general solution form, so we'll go ahead and write that. X is going to be C1 times the first vector, 2, negative 1 times the cosine of B, which is 2t, minus the imaginary vector times the sine of 2t. And then that's going to be times e to the 0t. So that's really a 1. I'll write it, but eventually we'll drop that. And then in the second term, we've got C2, and we take the imaginary vector first, cosine beta t, minus the, or sorry, plus the real 2, negative 1, and then sine 2t, also times e to the alpha t. So writing it one more time, we would have just C1, 2, actually, let me write it kind of the combined way, C1, and we'll have 2 cosine 2t, minus 2 sine 2t. On the bottom, we have negative cosine 2t. And then that's just times e to the 0, which is 1. And then we're going to have this c2. And we'll have, let's see, 2 cosine 2t plus 2 sine 2t. And on the bottom, it's negative sine 2t, also e to the 0. Okay, so there is the solution, the general solution. Now, to go to the next step, we need to establish what the constants are, which means we're going to have the initial condition. So the initial condition was specified above. Let me change that to green here. The initial condition was x of 0 is 2, negative 1. Sorry, 2, negative 1, which essentially means that when t is 0, x is 2. And when t is 0, y is negative 1. So I could take each of those equations separately, right? Let's do that. So the x equation is x as a function of t is 2, well, let me do it this way. It's going to be 2 times, let's do it the way it's written, c times 2 cosine 2t minus 2 sine 2t plus c2 times 2 cosine 2t plus 2 sine 2t, which means if I use this initial condition, this is a 2 whenever the time is 0, cosine of 0 minus 2 sine of 0, plus c2 times 2 cosine of 0 plus 2 sine of 0. And I know some things here. I know that cosines of 0 are 1, and sines of 0 are 0. So we end up getting that 2 times C2, 2 times C1 plus 2 times C2 has to equal 2, right? So that's one equation. And then the other equation, I'm going to need the y. So let's use the second row up here, second row values. So y as a function of t is negative c1 cosine 2t minus c2 sine 2t. So using the second the second initial value, that when t is 0, y is -1, so -1 here, when t is 0, minus c2 sine of 0, and then using the fact that cosine of 0 is 1 and sine of 0, gives me negative c1 equals -1. So right off the bat, I know c1 is equal to 1, okay? And then I can back substitute in this one and say, okay, so 2 times c1, which is 1, plus 2c2 equals 2. Divide everything by 2, and we would have 1 plus c2 equals 1, or c2 must equal 2. Is that right? Wait a second, they have to equal 0. So let me back off, I'm going too fast here. If I subtract 2 from both sides, I have 2c2 equals 0. So actually c2 must equal 0. Good. All right, so finally, I can write this now in a general form. X, or in a specific form, is the c1 value, which is 1, times the 2 cosine 2t. You know what, let me make that a better color. So x is going to be c1, and then times 2 cosine 2t minus 2 sine 2t, and then on the bottom it's negative cosine 2t, and then plus 0, right? This term is 0 because c2 is 0. So it's just this. This is the expression right here. All right, so then we could go ahead and plot the phase plot for that. So let me bring up the calculator, and we'll enter this in for that. So let me go back to the plot here. I'm going to clear off those ones from the previous problem. And for the x, we'll enter it as 2 cosine of 2t, close parentheses, and then minus 2 sine of 2t. Okay. And then for the y, it's going to be negative cosine of 2t. So this is probably a little bit simpler. I see there's no e to the t, and we don't have an exponential, either an exponential growth or exponential decay. So instead of that spiral we got last time, I'm thinking this is going to have kind of more of a constant radius, but the cosine and the sine are going to probably make either an ellipse or a circle of some kind. Okay, so there was a suggestion here for what the window could be, because I played around with this to try to get it so it didn't take too long to graph, but you still get a decent graph. So let me show you that. If we change our window now to go from 0 to 10, but only go up by 0.1 at a time for t, it's a little coarser, we can set the minimum at -5 and the max at 5, because this stays closer to the origin, and then also have from -5 to 5. And then when we graph it, we'll go ahead and do zoom square again. The zoom square is 9. Now you see how it's kind of overwriting itself, right? But it's staying right there because there's no e to the 2t. It's not getting larger each time. So it's just over and over again tracing out an ellipse. And it was going, if you watch carefully, in this direction, right? This is the direction that came up there. All right. So there's no like definite stable value, but it orbits, right, in one particular region. It doesn't get closer to the origin, it doesn't get farther away, no matter what t is, it stays on that locus of points. All right, so that would be the phase portrait there. So I don't know if I even had any homework for this section. It's not something we're emphasizing on the test, but I did want to talk about it because when we get to the section later on octave, it's important to know what these things look like. All right. So that would be the last day that we're going to spend on 8.2. When we get to the next section, 8.3, we'll start talking about what happens if we have a non-homogeneous system, where we have additional terms in the right-hand side that involve t.